Can an electron ever be found inside the nucleus of an atom? And if so, what happens? At first glance, it sounds impossible. The nucleus is tens of thousands of times smaller than the whole atom, and it's already jam-packed with protons and neutrons. If electrons were somehow tucked away inside the nucleus, there would be nothing left to give atoms their chemical structure, their ability to form the material world. But quantum mechanics doesn't play by our everyday rules. In this strange framework, particles don't follow neat little trajectories like billiard balls. You can't in general pin down both an exact position and an exact momentum at the same time. Instead, the best you can do is describe the particle with a wave function, and the wave function tells you the probability of finding the particle in different regions of space. The wave function itself evolves in a precise deterministic way, but the moment you make a measurement, the outcome is fundamentally probabilistic. In other words, the classical picture of certainty is gone. In its place, quantum probability rules the game. And there are deeper restrictions too. Heisenberg's uncertainty principle tells us that if you try to squeeze a particle into a smaller and smaller region of space, its momentum becomes wildly uncertain. Perfect confinement just isn't possible. So here's the puzzle. If we take those rules seriously and we define inside the nucleus as that tiny sphere of space occupied by the protons and neutrons, just a few femtometers across, what does quantum mechanics actually predict? Is the probability of finding an electron there strictly zero or just very small? And what exactly does the uncertainty principle have to say about this? That's what we're going to work out. First, we will quantify what inside the nucleus actually means, then write down the wave function to describe the electron, and finally, we will use the wave function to calculate the probability that the electron is found within the nuclear volume of space. Okay, so let's begin. The first point to appreciate is that a nucleus is not a mathematical point. It has a finite size. Scattering experiments starting with the famous Rutherford gold foil experiment revealed that the nucleus is incredibly small, typically of order 1 femtometer, where 1 femtometer is 10 to the minus 15 meters. For an order of magnitude estimate, it makes sense to start with the simplest atom, hydrogen, whose nucleus is just a single proton. And for simplicity, we'll take inside the nucleus to mean within a sphere of radius 1 femtometer, centered on that proton. So the real question is this: if we measure the position of the electron, what is the probability that the outcome lies inside that tiny spherical volume? And to calculate this probability, we first need the electron's wave function. When I'm researching for my own videos, I like to trace ideas back to their origins, looking at the original papers and stories of the pioneers. But what about our own origins? I partnered with MyHeritage to explore my own ancestry, taking their DNA test so I could share the results with you. You can get their DNA kit for just $29 by clicking the link in the description or scanning the QR code on the screen and using the coupon code PHYSICS. MyHeritage has a strict privacy policy. They never sell or license your data, and the kit is easy and simple to use. It took me just a couple of minutes. You do a quick cheek swab, pop it in the envelope, send it off, and then it's just a matter of waiting for your results. Okay, so what am I expecting? Well, I was born in Cape Town, South Africa. My mother was from England and my father was South African and his grandfather was Scottish. So I'm expecting to see maybe some South African, Dutch, Scottish and English. Okay, so my results are in. This is very exciting. Andrew, you are 30.6% Dutch. Okay, that is kind of in line with what I expected. 23.5% English, so that'll be on my mum's side. Okay, that makes sense. Okay, we've got 16% Scottish and Welsh, so that'll be my father's grandfather, I think. French, 11.9% French. I would not have thought that. Okay, so we can take a more detailed look into my ethnicity by clicking on the Ethnicity Estimate tab, and then we see here on the left-hand side, we have a much more detailed breakdown of my ethnicity percentages. Very interesting. Another really cool feature is the DNA Matches tab. If you click on that, you can see that I have 11,727 DNA matches, and this tab allows you to look at relationships and probable relationships with people around the world, including shared DNA percentage. And this has led to some really interesting conversations with my dad about my own heritage. So if you would like to find out more about your origins and your ancestry, then I highly recommend My Heritage. Just click on the link in the description or scan the QR code on the screen and your journey can begin today. In quantum mechanics, the wave function encodes everything we know about the system, and we can obtain the wave function by solving the Schrödinger equation, which takes the following form, where for the simple case of hydrogen, the potential energy is given by the Coulomb potential. The negative sign simply tells us that there is an attractive force between the proton and the electron. When we solve this equation, we find the famous hydrogen wave functions, clouds of probability that provide information about where you're most likely to find the electron if you measure its position. For the hydrogen ground state, also known as the lowest energy state, the wave function has the following form, where the constant a is the Bohr radius, about 5.3 times 10 to the minus 11 meters. Its appearance in the wave function sets the characteristic size of the atom. The prefactor, 1 over the square root of pi a cubed, is called the normalization factor. It ensures that the total probability of finding the electron somewhere in space, anywhere from r equals 0 to r equals infinity, is exactly equal to 1. We can plot this function to better understand its shape. In the first subplot we see how the wave function varies with radial distance, and in the second we see a heat map showing how the wave function varies across a two-dimensional slice through the hydrogen atom. We see that the wave function peaks at the centre of the atom, at r equals 0, and decays exponentially as r increases. Okay, so what does this wave function actually tell us? Well, if we take the modulus squared, we obtain the probability density. This is the probability per unit volume of finding the electron at a particular point in space. That means that the probability of finding the electron in a small volume element dV is equal to the modulus squared times dV. But often we want to know the probability of finding the electron at a certain radial distance from the nucleus, or within a given range of distances. To find that, we need to account for the fact that the amount of space available grows as we move outwards from the centre of the nucleus. First, we note that all points that are at the same distance r from the nucleus lie on the surface of a sphere of radius r. If we imagine a thin spherical shell of thickness dr, then the volume of that shell is the surface area of the sphere, 4 pi r squared, multiplied by the thickness dr. And therefore the probability of locating the electron within that thin shell is equal to the modulus squared of the wave function multiplied by the shell volume, and this is equal to the following blue expression. Next, if we sub in the ground state wave function for hydrogen, we end up with the following expression, and this represents the probability that the electron will be found in the thin shell between r and r plus dr. By convention, this is written as P of r dr, where P of r is known as the radial probability density. If we plot P of r against r, we see that it's 0 at r equals 0, and it rises to a peak at r equals a, which, if you recall, is the Bohr radius, and then it decays exponentially as r increases. And here is the key point. If we want to find the probability that the ground state electron is located between two radial distances r1 and r2, then we simply need to find the area under the curve between these two locations. In other words, we need to integrate the radial probability density with respect to r between r1 and r2. Okay, so we now want to use this approach to determine the probability that the electron resides somewhere within the volume of space occupied by the nucleus. To see this more clearly, we can plot the radial probability density and then rescale our axes and zoom in. At a radius of about 10 to the minus 15 meters, our order of magnitude estimate for the nuclear radius, there is indeed a small area between the radial probability curve and the x-axis. This tiny area is what we must calculate if we want to determine the probability of finding the electron in this region of space. So, although the area is small, it's not 0, which means there is a chance the electron can be found here. Okay, so we can now state things in mathematical form. The probability of finding the ground state electron between r equals 0 and r equals capital R, where capital R is the nuclear radius, is given by the following purple expression, and we can then pull out the constants to neaten things up a bit. And so we see that the whole problem boils down to evaluating the integral of r squared e to the minus 2r over a between 0 and r. Now let's label this integral I, and our task is to evaluate it. To do so, we can integrate by parts, making use of the general result. In our case, we set u equal to r squared and dv equal to e to the minus 2r over a dr, which immediately gives us du equals 2r dr and v equals minus a over 2 e to the minus 2r over a. If we then integrate by parts, we arrive at the following purple expression. After substituting the limits, this becomes the following blue expression. Notice that with just one integration by parts, we've already reduced the powers of r in the integral. To continue, we integrate by parts once more, this time using the following change of variables. Carrying out the integration and applying the limits gives us, at last, this glorious green expression. Okay, so now that we've dealt with the integral, we can substitute this result back into the equation we wrote down for the probability. Doing so gives us the following beautiful blue expression. We can simplify further by multiplying out the bracket, and we end up with a compact equation for the probability in terms of the nuclear radius, capital R, and the Bohr radius, a. Now, we can neaten things up a bit further by defining x equals 2r over a, which makes our probability equation look a little less cluttered. And this is the expression we were aiming for, the exact equation that gives the probability of finding the ground state hydrogen electron in the region between r equals 0 and r equals capital R. We see that it depends only on the nuclear radius and the Bohr radius. Often it's convenient to note that the nuclear radius is much smaller than the Bohr radius. In that case, x equals 2r over a is much less than 1, and we can expand the exponential term as a Taylor series, keeping only the first few terms. If we now substitute the Taylor expanded exponential term, we obtain the following blue expression. Expanding out the brackets shows that the leading term is x cubed over 6, with higher order terms that can be ignored since x is so much smaller than 1. And so we arrive at a greatly simplified approximation for the probability of finding the electron within the nuclear radius. If we then recall the definition x equals 2r over a and sub this back in and simplify, we arrive at the remarkable result that the probability of finding the electron within the nuclear radius is approximately 4/3 times capital R over a all cubed. And we see that once the dust has settled, the probability of finding the electron within a radius r scales with the cube of the ratio of nuclear size to atomic size. Now, before plugging in the numbers, it's worth noting that there is a neat alternative way to see this relation, which is quicker and avoids the tedious integration by parts. The trick is to look at the plot of the modulus squared of the ground state wavefunction. If we zoom in right down to the scale of the nucleus, we see that it's essentially flat across such a tiny region of space. In other words, within the nucleus, we can safely approximate it by its value at the origin. Okay, so why does that help? Well, if you recall, the probability density multiplied by dV gives the probability of finding the electron inside a small volume element dV. Because the nucleus is so small compared with the Bohr radius, the wave function hardly changes across it. That means we don't need the full integral. Instead, we can estimate the probability as the probability density at the origin multiplied by the nuclear volume. Now, as we've already seen, the hydrogen ground state wave function takes the following form. From this, we can construct the probability density, which is simply the modulus squared, and then we see that at the origin, this will be equal to 1 over pi times a cubed. And if we sub this into our probability expression and simplify, we find that the probability is roughly equal to 4/3 r over a cubed, which is exactly the same result as before, but just in a few lines and without the integration. Okay, so now that we have an approximate expression for the probability, Let's actually estimate it. The nuclear radius, as we said, is around 1 femtometer, while the Bohr radius is about 5.29 times 10 to the minus 11 meters. Plugging these values into our probability equation, we find a probability of around 1 times 10 to the minus 14, which is about 1 part in 100 trillion. Now, that's not zero, but it's absurdly small. And yet, this tiny overlap isn't irrelevant. It contributes to subtle shifts in the electron's energy levels, such as the Darwin term in the fine structure and the Fermi contact term in the hyperfine structure of hydrogen, and it even sets the scale for processes like electron capture in certain heavy nuclei. But this isn't the whole story. So far, we've only looked at the simplest atom, hydrogen. But what happens in heavier atoms packed with many protons, neutrons, and electrons? The key idea is that the innermost electrons see almost the full nuclear charge. Outer electrons are screened by the rest, but the very first shell has nothing between it and the nucleus. And so, to a good approximation, the inner shell electrons behave a bit like the electron in a hydrogen atom, but experiencing a nuclear charge Z instead of just 1. In this simple model, the effective Bohr radius scales as A divided by Z, where A is the Bohr radius in hydrogen and Z is the number of protons. That's not the full story. Real multi-electron atoms have electron-electron repulsion, relativistic corrections, and more, but this scaling captures the leading effect. As Z increases, the inner shell electrons are pulled dramatically closer to the nucleus. And since our overlap probability scales as R over A cubed, even a modest decrease in A makes a huge difference. Okay, so let's make this concrete. Take iodine with 53 protons and a nuclear radius of around 6 times 10 to the minus 15 meters. In the case of iodine, the effective Bohr radius comes out at around 1 times 10 to the minus 12 meters. And if we use this value along with the larger nuclear radius, then the probability of finding the inner shell electron inside the nuclear volume comes out at around 3 times 10 to the minus 7. Now, that's still very small, but notice it's about 8 orders of magnitude larger than in the hydrogen case. And if we take gold as another example, with Z equals 79 and a nuclear radius of around 7 times 10 to the minus 15 meters, we see that the effective Bohr radius is smaller still, at around 6.7 times 10 to the minus 13 meters. And this leads to a probability of approximately 1.5 times 10 to the minus 6. Okay, so what does this all mean? Well, for hydrogen, the overlap was tiny, but in heavier elements, the overlap grows by many orders of magnitude due to the stronger attraction from the positively charged nucleus and the larger nuclear radius. This effectively reduces the average distance between the inner shell electrons and the nucleus, producing greater wavefunction overlap and therefore a much higher probability of the electron being found inside the nuclear volume. Okay, so does this higher probability actually have any observable effect in larger nuclei? Well, as you know, inside the nucleus, protons and neutrons are held together by the strong nuclear force. But the weak nuclear force is also present, and it allows protons to change into neutrons. One way this happens is through electron capture. In this process, a proton in the nucleus captures one of the atom's inner electrons. We can write this process in the following way. This is telling us that a proton and an electron combine to make a neutron, and an electron neutrino carries away the energy and momentum. And this process is due to the weak interaction. Now, 2 ingredients have to line up for this to occur. The first is energy. The reaction can only proceed if the total energy of the initial state is at least as large as the total energy of the final state, counting rest masses, nuclear binding, and kinetic energy. If the final state would require more energy than the initial state provides, the reaction is forbidden, no matter how much overlap there is. That's why a proton never spontaneously captures an electron in isolation. In energy terms, the rest mass of a free neutron is about 0.782 megaelectronvolts larger than that of a proton plus an electron. The tiny 13.6 electron volt binding energy of the hydrogen doesn't come close to bridging that gap, so the process is energetically impossible. But in many heavier proton-rich nuclei, the situation is reversed. There, turning a proton into a neutron can lower the total energy because it reduces proton-proton electric repulsion while keeping the strong force binding largely unchanged. Crucially, this only helps if the change moves the nucleus towards its locally preferred neutron-to-proton balance. Push it past that balance and extra neutrons become costly. Now, that extra binding energy resulting from the proton changing into a neutron more than compensates for the neutron's larger rest mass, and the difference emerges as energy carried away by the neutrino. That's why isotopes like beryllium-7 and iodine-125 can and do decay by electron capture. We can think of this in terms of a NZ plot, where we plot neutron number on the x-axis and proton number on the y-axis. The stable nuclides are then shown in blue and represent what is known as the valley of stability. Nuclides which undergo electron capture are shown in orange. We can see that by changing a proton into a neutron, these nuclides can move closer towards stability. The second ingredient is wavefunction overlap with the nucleus. Once the energy condition is satisfied, the rate of electron capture depends on the electron's probability density inside the nucleus. In iodine, as we've already seen, the overlap is of order 3 × 10⁻⁷, which is tiny but still enough for the weak interaction to act. Hydrogen is stable because capture is energetically forbidden, not because the overlap is 0. In heavier proton-rich nuclei, both conditions hold. The decay is allowed, and the small but finite overlap supplies electrons at the nucleus. And all of this raises an interesting question. If electron capture needs an orbital electron at the nucleus, how do electrons come out of nuclei in beta decay? Were they sitting inside all along? If you recall, in beta decay, electrons appear to be emerging from the nucleus, which makes it look as if electrons might have been sitting inside the nucleus all along, waiting to be released. That raises a natural question. Can an electron simply live inside a nucleus? This idea isn't new. In the early days of nuclear physics, many physicists thought exactly that. Because nuclei were seen to emit electrons in what we now call beta decay, the obvious guess was that those electrons were already hidden inside. But the idea quickly runs into trouble, and the trouble has a name: the Heisenberg uncertainty principle. This fundamental principle of quantum mechanics can be stated as delta x times delta p is greater than or equal to h bar over 2, where delta x is the uncertainty in position, delta p is the uncertainty in momentum, and h bar is the reduced Planck's constant. This relation is telling us that there is a fundamental limit to how precisely we can simultaneously know a particle's position and momentum. So let's now apply this to the electron. If we try to confine an electron to the size of a nucleus, then we can take delta x as being roughly equal to the nuclear radius, which we will take as 1 femtometer. Okay, so what is the momentum uncertainty in that case? If we rearrange the uncertainty relation for delta p, we find the following expression. Then, using delta x equals 1 femtometer, this gives delta p as being roughly equal to 5.3 times 10 to the minus 20 kilogram meters per second. Now, that might look small, but for an electron it's huge. Large enough that relativistic effects matter. So the question is, what energy corresponds to this momentum? To answer this question, we need to use the relativistic energy-momentum relation. Using the momentum from the uncertainty estimate and the mass of an electron, we find that the electron's energy is approximately 1.59 times 10 to the minus 11 joules. If we then convert this energy into electron volts, we find a value of around 100 MeV. So if you squeeze an electron into a nuclear-sized region, it has to carry energy on the order of 100 MeV. Confinement drives up its momentum and therefore its energy, and we can plot this information. As the confinement distance shrinks towards nuclear dimensions, the energy implied by the Heisenberg uncertainty principle rises sharply and reaches around 100 MeV when the confinement length is around 1 femtometer. And here's the key point. When we actually perform experiments to measure the energies of electrons emitted in beta decay, they are nothing like this. Rather, we find that beta particles typically have energies of a few hundred kiloelectron volts, sometimes a few megaelectron volts, and at most around 10 MeV. That is still an order of magnitude smaller than the 100 MeV required for a nuclear electron. And this energy mismatch is decisive. If electrons really lived inside the nucleus, the uncertainty principle insists that they'd be confined with around 100 MeV of energy, and if released, they'd emerge with roughly that amount of energy. But we don't see that. Beta particles come out far less energetic, and so the only consistent conclusion is that the electrons in beta decay were not pre-existing prisoners of the nucleus. Instead, in beta minus decay, the weak force lets a neutron transform into a proton, an electron, and an antineutrino. The electron is created at the instant of decay. It isn't a long-trapped particle escaping. And the antineutrino carries off part of the energy and momentum, giving the continuous beta energy spectrum observed in experiments. And again, we can understand why this process is favourable by looking at the NZ plot. If we highlight the locations of all nuclides that undergo beta minus emission, they tend to lie on the neutron-rich side of the stability band. And by undergoing beta minus decay, they trade a neutron for a proton, moving closer towards the stability line. Okay, so to bring this full circle, can electrons truly live inside the nucleus? The answer is no. The overlap of the electron's wave function with nuclear space is real but tiny, just enough to enable processes like electron capture and leave their imprint on subtle energy shifts. And in beta decay, the electron isn't a long-trapped resident escaping, but a brand new particle created by the weak force, with the neutrino carrying away the balance of energy. In the end, quantum mechanics gives us a clear and consistent picture. Electrons may occasionally visit the nucleus, but it can never be their permanent home. So before we end, just a final shout out to today's sponsor, MyHeritage. If you would like to find out more about your origins, then just click the link in the description or scan the QR code on the screen and use the coupon code PHYSICS. And as always, a massive thank you to all my patrons and a special shout out to the following who have been incredibly generous with their support. Thank you so much. I couldn't do it without you.